one little bit of information I would like to give you about my videos. Since we have a whiteboard here, and often I am in front of the board, what I will always do in these videos is that in the beginning and in the end there will be sufficient time when I will not be there between the board and the camera, and during that time you can take screenshots so that you can take notes from these videos for your future reference. Now moving on, we are going to discuss the process of estimation of errors, estimation of true values, and also we will learn how to express errors. Now, when we do a physical experiment, we take a whole number of readings. Now, suppose you're measuring some physical quantity, say x. What you do is you take lots of readings, x1, x2, x3, and so on, all the way up to xn. So we've taken n readings of a particular physical quantity which we are trying to measure. Then we estimate its true value, and true value is always estimated to be the mean value. So we take a lot of readings and take a mean, and that mean represents for us an estimate of the true value. Now, larger the number of readings, smaller the random error. Another assumption we make here is that we have been able to completely eliminate the systematic error by taking care of any system flaws in our process of measurement. And so what we are left with at the end of this process of estimating a true value is the leftover random error, which we have tried to reduce by taking lots of readings, but some will still remain. Now, in these readings, there are individual errors. Each of these readings is somewhat different from our estimated true value. And so the error in each one of these individual readings can be calculated. For instance, in the first reading, the error would be x bar, that's the estimated true value or the mean value, minus the value x1. We always take a mod of this. So the error in the first reading is the true value minus the measured value. You can always do the opposite. Since it's a mod, doesn't really matter. So the error in the first reading is x bar minus x1. We express this as delta x1. Similarly, the error in the second reading is x bar minus x2 mod. That's x delta x2, and so on and so forth. In the nth reading, therefore, the error is delta xn, which is x bar minus xn mod. Now, the estimated error in this measurement is the mean of the individual errors. So we take a mean of all these individual errors, delta x1, delta x2, etc., etc. We add them up and divide by the number of readings to get an estimated error. Now, when we express the measured quantity, the way it is expressed in physics always is x bar plus minus delta x. That's the error. So here what we are really saying is that the measured value x actually lies in a certain range. We can absolutely never get to the absolute true value. We can only report a certain range. The measured value, we say, lies in this range, and that it is going to be definitely greater than x bar minus delta x, and it will be less than x bar plus delta x. So x lies in this range, and that's all we report. We do not say that x has this specific value. Now, the way we express errors, now if we just express the error as this delta x that we've estimated, the estimated error, if we are expressing the error simply as this delta x, we say we've expressed the absolute error. If we divide delta x by x bar, we call it the relative error or fractional error. This is also called, this method of expressing the error is sometimes also referred to as accuracy. Now, why we refer to this as accuracy is that when we compare different measurements, then the accuracy is always compared from one measurement to the other. The accuracy is always compared by comparing the relative error or the fractional error and never the absolute error. For instance, if we make a measurement of 1000 meter and we get to know that there is an error of 1 meter there. Now 1 meter appears to be a fairly large error. And suppose we make a measurement of 1 centimeter in which there is an error, absolute error of 1 millimeter, then the 1 meter error is so much larger than the 1 millimeter error. In absolute terms, the 1 meter error is so much bigger. But when we compare the two measurements, the first measurement of 1000 meter with the 1 meter error, the relative or the fractional error is 1 divided by 1000. Whereas in the other measurement of 1 centimeter with the 1 millimeter error, we have an error, a fractional error of 1 by 10. Now, in fractional terms, the error in the second measurement, where the error was 1 millimeter in a reading of 1 centimeter, that's the bigger error, and therefore that's the less accurate measurement. Another way we can express errors is a percentage error, where we express delta x as a percentage of the mean or the true value. And these are the three ways we generally express errors. So that's estimation of errors and the expression of errors. Very often in examination situations, a whole lot of reading data is not provided. And in those situations, what we tend to do is we take the least count to be the error. And often when that is also not known, we assume the least count to be an increment of 1 in the last digit of the measured value. For instance, there is some measured value that says 2.05 meter. Then a change of 1 in this last digit represents our estimate of error. If the least count is provided, we take that to be the error, and if data is provided, of course, this is how we estimate. This is one method of estimating errors. There can be others. For instance, errors are actually better estimated by taking standard deviations rather than the absolute deviations that we have taken here. But more often than not, we stick to this process of estimating errors. Thank you very much.